Thank you, everybody, for joining us today. We're really excited to have our speaker, Dr. Frank Heitmuller, with us to give the SEDS Online webinar for this month. Frank got his bachelor's degree from Florida State University before heading over to UT Austin for a master's and a subsequent PhD. Frank works in the realm of sedimentology and geomorphology, and with a heavy focus on fluvial systems, which you can probably guess from the title slide that you're seeing here. And he's going to talk to us today about the lower Mississippi River and some of the work he's been doing over the last, sounds like 15 to 20 years. So Frank, thank you so much for joining us, and I will give you the floor.
Great. Well, thank you, Dr. Pedersen and Drs. Lokier for inviting me to participate in this SEDS Online webinar series. It's exciting to be able to share some of the research that we've been doing with you here on the lower Mississippi River, as Dr. Pedersen mentioned, over the last 15 or so years. And in Paul Hudson's case, who's my co-presenter from Leiden University, has been working on the lower Mississippi in this study area since his PhD dissertation back in the 1990s. And so we really are building upon a legacy of some of the research that's been done here at the close to and just above the apex of the delta before it goes out into distributaries, making its way out into the Gulf of Mexico. So I'll go ahead and start off with just a little bit of information about the lower Mississippi drainage. As you can see right here, it's the third largest drainage in the world. Of note to this talk is that more than half of the watershed drains more subhumid to semi-arid zones of the central and west central North America here. In the eastern side of the watershed, the Ohio River primarily and the Tennessee drain more of a humid part of the watershed. So you've got a lot of just natural diversity that all gets funneled in as the river moves south to the deltaic apex right here in the vicinity of a city called Natchez, Mississippi. We'll talk a little bit about the Old River Control Complex that obligates about 30% of the Mississippi River's discharge into the Atchafalaya distributary, leaving about 70 or so percent of the remaining sediment and discharge to go past Baton Rouge and New Orleans. And so we're literally at kind of the mouth of the funnel here, where our study areas are located, that captures, of course, all of the variability of the watershed further upstream. So to focus in a little bit more in our study area and talk about some of the different controls of sedimentology here on the lower Mississippi, there's been a legacy. It is one of the most heavily engineered and regulated river systems on Earth. Notably as a result of infamous flooding up here in northern Mississippi and Arkansas during the 1927 and 1937 floods, which prompted federal legislation resulting in the Mississippi River and Tributaries Project, where levees that were relatively low were increased in height, notably, were more lined the channel. You can see right here the red solid lines. I know it's a little bit faint, show the location of main stem levees that basically have narrowed the width of the effective Mississippi River floodplain to a much narrower corridor than it once used to be able to inundate. And so that's a very important part of the research questions that we ask in association with our project is how have the legacy of river engineering manifest itself historically since the mid 20th century all the way to present, right here at the apex of the delta where we're located before that sediment gets distributed in different directions. And so that's a large overarching question that prompts some of our investigations that we've done. In the vicinity of our study area, the levees are about 9 meters above floodplain level, and they're intended to accommodate a flood that would be 10 to 30% greater than the infamous flood of 1927. In addition to the levee system that's been constructed, a series of channel cutoffs, meander bend cutoffs, were made in the 20th century that shortened the river by over 240 kilometers. And of course, the energy gradient, the slope and gradient of the river have increased as a result of that, certainly mobilizing considerable quantities of sediment. And then through the decades, that sediment has translated downstream the channel. And then finally, I want to mention the role of revetments. These are within the narrow embanked corridor, another measure that have basically articulated mats that have been put on the banks of the river to prevent lateral migration and another potential source of sediment. So the river channel is fixed within a much more narrow embanked corridor. So some of the issues that we need to think about with this in mind through the years are shown in kind of a fairly simplistic diagram here, where we have a natural channel with natural levees that can inundate wide areas of a floodplain. And when dikes or artificial levees are installed to prevent flooding, we now, of course, constrain the discharge and the sediment load within a much narrower corridor. In some cases, this results in rapid rates of vertical floodplain accretion that could potentially be followed by channel bed aggradation and the entire river system and its surrounding embanked floodplain being elevated to a higher level above the former floodplain that is no longer active. So this is of great concern because when you take into consideration aggradation within the actual artificial levee system, that of course can lead to conveyance loss of floods and could propagate flood hazards in the area if allowed to go unchecked for decades on end. We've also seen within the channel some evidence here of channel bed aggradation, this bathymetric profile showing anomalously wide and extensive shallow areas of the Mississippi River right in the vicinity of the control structure that obligates that 30% approximately of water and discharge into the distributary of the Atchafalaya. And so that kind of prompts this overall title of this talk, the Clogged Sieve. Are we seeing effects of sedimentation in the vicinity of the deltaic apex on flooding conditions in the Natchez area and potentially further downstream? And that's some of the questions that we'll be investigating here. So despite the more narrow width of the floodplain, and in this Google image, you can see the artificial levee, this white solid line on the eastern or the western Louisiana side of the river. And then we have inundated floodplain extending from the levee all the way over to what's called the bluff line in Mississippi on the eastern side of the river, marking the edge of the Mississippi River Valley. In between those two barriers to flooding, we do still exhibit all of all of the different types of sedimentary environments you would expect of a textbook meandering river system, including natural levee deposits that are elevated along the banks of the river, crevasses that are breached that allow for relatively coarse-grained sediment to be spread into distal, fine-grained, lower-lying back swamp deposits, oxbow lakes and abandoned channels that have been plugged through time with sediment, and point bar deposits, meander scrolls as they're referred to, marking deposits laid down by lateral migration of the river before revetments were installed that basically restrict the lateral migration today. So getting into why we're investigating this from a flood perspective, what we're taking a look at here in these graphs are stages observed throughout the water year at Natchez just upstream from the study areas. The solid lines indicate major tributaries to the Mississippi River that were responsible for the observed annual hydrographs. And so the blue line is the water-laden Ohio River from the humid side of the basin. And then we see some of these other more warm colors representing the upper Mississippi River, the Missouri River, and the Arkansas River, draining more of the subhumid to semi-arid regions of the watershed. So you can see the Ohio River always pretty much is the main contributor toward flooding downstream the lower Mississippi River at Natchez in almost all cases, within sometimes supplementation by some of those other tributaries draining the less humid side of the drainage basin. So through water years 2001 to 2020, 6 of the 10 highest stages on record were observed at Natchez. And so once again, that kind of leads us into, is this a sediment clogged type of an area? Or is this more related to hydrologic changes and climate change through time, or some combination of both? Why are we getting more intense flooding, more frequent flooding along this reach of channel? Among these floods, we can see in 2011, that was the highest crest on record, actually exceeding the 1927 flood down at Natchez in particular, of about 19 meters, according to the local stage datum there, and the 2019 flood, which was the longest duration on record for over 213 days above flood stage. So we're going to be taking a look at a number of these different floods and some of the activities that we were able to get sediment samples following the floods, and in the case of the 2019 flood, in the overbank water column during it, to be able to see what's going on with the sedimentary dynamics. To also kind of show how the flood regime is somewhat changing through historical time frames. At Natchez in particular, we can see that both annual high and annual low flows on Natchez have been increasing since the early 20th century to the modern contemporary time frame here, where you can see a number of those floods that are clustered here toward the end of the graph. Also want to point out here the 1973 flood, we'll get back to that, was also a prolific flood that followed a few decades of not much flooding. And so that leads into some questions about sediment availability and how that flood deposited sediment in the floodplain. We can also see here that flood durations at Natchez have tended to increase, where a number much more extensive long-term floods that stay overbanked for long durations of time. And when we compare those flood durations even to the next gauging station upstream near Vicksburg, we see that Natchez is a more disproportionately flooded type of an area relative to Natchez by consistently being plotted below the line that would mark equal duration of flooding between upstream and downstream. So we're seeing problems with flooding down at Natchez, and there are also other contemporary problems that many of you are aware of with lower Mississippi River discharges and sediment. That includes documented declining suspended sediment loads in the lower Mississippi River as a result of upstream dams and regulations along some of the major tributaries. So the sediment loads are declining while we're also confining the river between those in the embanked floodplain between artificial levees, which doesn't allow for that suspended sediment to effectively mitigate against coastal land loss in Louisiana. Nutrient loads, of course, that extend out into the Gulf of Mexico, causing hypoxic zones in other types of restoration projects of floodplains further upstream. So the lower Mississippi River, our study areas are focused. Here's the old river control complex, marking the apex of the delta, where again about 30% of the Mississippi River water discharge is diverted to join the Red River that then makes the Atchafalaya River that moves downstream and empties into the Gulf of Mexico at a separate a location west of the current Mississippi River's mouth downstream from New Orleans. These are, of course, again, have all of the different sedimentary environments we would expect of a meandering river system, just more trapped within a narrower embanked corridor than we see today. So what are the conditions? One of the kind of questions we had was during a flood or during multiple floods in the case of what we were able to capture here, what are the conditions of flooding that would then be responsible for floodplain sedimentation in different sub-environments of the Mississippi River in these embanked floodplain corridors? And so we installed water pressure, water level sensors, and water temperature sensors at a number of locations across these embanked floodplains, including back swamp environments, ridge and swale, meander scroll environments, and an oxbow lake, to monitor some of the conditions of overbank inundation that we would expect to find and how this might end up influencing sedimentation in different parts of the floodplain. So just to kind of see an example of how these data were able to allow us to interpret how much energy and how long and what parts of the overall flood hydrograph areas of the floodplain were inundated, we are fortuitous in that the installation of these sensors were able to capture major flood events in 2018, 19, and 20. And the way that these graphs are designed is that the gray background is an annual hydrograph of the actual Mississippi River channel at Natchez, just upstream from where these sensors were installed in the overbank floodplain environments. The solid lines represent the water levels that were recorded by those sensors just downstream from Natchez. And then the more dashed and stippled lines that we see here record the same water level temperatures in those floodplain environments as well. And so all of these floods, as we can see, started basically in the winter during spring storms, winter snowmelt, and that was where the hydrographs were initiated. And so that then proceeds through the summer into the spring and into the summer where the hydrograph began to decline. And you can see, of course, an overall increase in the water temperatures. By investigating basically the relative timing between water level increases in the floodplain and the water level temperatures recorded in the floodplain at the same time, we were able to basically detect the overall patterns of inundation that we see during a major flood event from the rising limb all the way through the falling limb of the hydrograph. Number one, areas that were relatively low-lying water bodies in the floodplain, like the Oxbow Lake Mary right here, were the first to begin to rise and the last to recede during the falling limb of the hydrograph. And basically, we know that the elevation of the periphery around these oxbow lakes was higher than the water levels in the river that were responsible for the rise in the oxbow, implying that there was a subsurface seepage component from the river connecting to the oxbow lake that resulted in the first detectable rises in the floodplain environment. A few days thereafter, as the water levels continued to rise in the river, we were able to find that backwater inundation coming up these low-lying Yazoo tributaries would push water into the more distal, low-lying parts of the floodplain. One of the interesting things that water temperatures indicated is that we began to see water level rises as those waters backed up and moved upstream into these distal low-lying areas. But the water temperatures that were recorded in these areas did not actually fall down to relatively cold waters that were experienced in the river channel. So what we're seeing is that water was actually being moved across some of these open floodplain environments and maintaining the warmth of the overall surface of the ground. In some areas, these were completely fields that didn't have any kind of shade to them. And so the water levels were rising while temperatures of the water were not falling substantially. And then we were able to detect as waters in the channel continued to get higher and higher, crevasses were activated that then made water that was much colder from the channel inundate some of those areas. We saw dramatic kind of declines in the water temperatures while water levels rose, and we began to see even higher level sensors began to experience some of those the inundation as well. So the overall sequence that we see here begins with subsurface seepage into these lakes, backwater inundation where water temperatures were relatively high, and then cold water that began to flow vertically over these different natural levees through natural levees, basically decreasing the water temperatures in the floodplain and then back out to the channel. So we're going to see how this plays out in terms of sedimentation patterns, but to understand that overbank hydrology is important. During the 2019 flood, we actually got out in a boat and were able to sample the overbank water column and match that to some of the readings that federal agencies were making on the river channel during the flood. We went out during relatively cold water conditions here in March and warmer water conditions here in late June. Both were during very high levels of major flood conditions on the Mississippi River. And we took a look at some of the different sediment concentrations and compared them to the main channel, both upstream and downstream. And what we found was that in the actual floodplain, approximately 2 to 5 kilometers away from the channel bank was where our sampling sites were located, considerably lower suspended sediment concentrations relative to the river channel. When we take a look at those same samples that we obtained, these again were depth integrated samples that were averaged over multiple sites across the embanked floodplain, we also noticed that adsorbed or particulate carbon on those sediments and particulate nitrogen were considerably higher than those levels that we saw in the actual river channel upstream and downstream. And so what that suggests is that sands, non-adsorptive, kind of chemically inert sands, were deposited within maybe 1 or 2 kilometers of the channel bank along natural levees as we would expect. And the remaining finer grain absorptive types of sediments, muds, continued across the floodplain, of course, at lower concentrations, but also with more carbon and nitrogen adsorbed to those particles moving across the floodplain. So it essentially shows that sand is deposited quickly, finer grain materials continue to move over bank. Very kind of weak linear trend lines also indicate that some of those muds, as they move across the floodplain, begin to flocculate and settle gently to the floodplain surface. We have anomalies that we can see that we can explain, and I can answer questions about that. But some of these more distal areas of the floodplain had some lower levels of some of this fine-grained sediment than you had further up the floodplain closer to the river bank. And so we do see drapes of mud that are deposited, but most of the fine-grained sediments are bypassing some of these areas during major flood events across the floodplain environment and rejoin the river channel. So that's going to explain some of the different types of sediments that we see deposited on floodplains by actually taking a look at what's in the overbank water column above. So now that gets us in kind of the main points of the main findings that we have of some of these different areas that we go all the way back to the major 2011 flood event in the same area. So in 2011, this is again the highest stage in recorded history. The Ohio River tributary was the one that was providing most of the river to the lower Mississippi, with lesser contributions from the upper Mississippi and Missouri rivers later on in the hydrograph. Also notice right here that before the major crest of the flood in this area, there was a little bit of what I'd call a pre-flood. It got just above flood stage and then it declined. And this also comes into question when we interpret the amount of sediment deposited in the floodplain. So Dr. Richard Kessel in 1973 went out to the study areas that I've been referring to. And this followed kind of an infamous 1973 flood that I pointed out a few slides ago. And he went to a number of overbank locations in the floodplain and sampled the thickness of the deposits and then took those samples back to the lab to analyze them for grain size. After the 2011 flood, the National Science Foundation funded a rapid study where Dr. Paul Hudson and I joined Dr. Kessel, who came up from LSU, to basically resample some of the same locations that he sampled following the 1973 flood. So he was kind of our quality assurance, quality control expert right here, making sure that we were sampling the exact same way that he did following that flood of 1973. So these are kind of showing our results in 2011. We can see that the wider the circle, white circle is, the thicker the deposit. And you can see most of these were less than 100 millimeters in thickness. Areas that you might imagine more distal from the channel would have been thinner deposits. Areas closer to the river channel were thicker, although you do see some anomalies like this slightly thicker deposit here right along the bank of this Oxbow Lake, which during a major flood was a fairly rapid flowing high velocity conduit for overbank water that pretty much continued natural levee deposition over here on this Oxbow Lake. So you can also see that we went down further downstream from the apex in this area and sampled similar types of conditions. The red dots show where we believe we exampled it close to the exact same location as Dr. Kessel did following the 1973 flood. So when we match and compare those two different samples, we note that there was considerably less overbank deposition in all of the environments. You can see natural levee more proximal zones to the river and back swamp zones more distal from the river. But thicknesses were considerably less in 2011 than a slightly lower magnitude flood was in 1973 in all cases. Notice here the meander scroll environments were considerably thicker in 1973, almost a meter on average, and we barely detected just a drape of some sediment on these particular deposits in 2011. So one of the things I want to mention is that in 1973, of course, that was a couple of decades where we did not have very many floods in this region of the river. We recall also that the cutoff programs upstream a few decades earlier probably contributed a lot of sand that migrated downstream the river channel, much of that sand being entrained by the major 1973 flood kind of swarmed over some of these distal kind of environments and, of course, proximal environments, leading to these very kind of profound thicknesses of the overbank deposits that we see. We also see that generally speaking, around natural levees and in distal environments, our sediment samples were coarser by a little bit, had greater percentages of sand in them. So what this indicates is that we potentially see deeper flows with faster velocities that are pushing more sand into some of these more distal environments than we experienced. But then the meander scrolls again were a little bit more of an anomaly, probably as a result of all of that sand availability in the decades following a low flood frequency period along the Mississippi River. So we're seeing a little bit of changes, and we'll come back to this later when we take a look at floods that occurred more recently in 18, 19, and 20. We'll go back and see how all of these compare to each other. So one of the reasons that explains the differences that we feel between 1973 deposition and 2011 deposition really comes back to the source area of those floods. So over here on the left, we see the Missouri and the Ohio rivers suspended sediment concentrations and discharges in 1973. Down below that, we see that the lower Mississippi River suspended sediment concentrations and discharges downstream from here. So the flood basically translated from upstream to downstream. Importantly, we see that the suspended sediment concentrations of the Missouri River, draining that more subhumid to semi-arid part of the watershed, were much, much higher than any of those that we saw here during 2011. We can also see that the Ohio River here was a much greater contributor toward the discharge of the flood event in 2011 than was experienced here in 1973. One thing that we note is that this was the flood here in April through May of 1973 along the lower Mississippi River. We did see what we would call a sediment exhaustion event preceding the crest of that flood where concentrations in the lower river were higher. But the thing is, we also saw that pre-flood bump before 2011, the big crest, we also had a similar exhaustion event. So we really can't attribute lower amounts of deposition in 2011 to this exhaustion event because we also experienced the similar sediment exhaustion event prior to the 1973 flood. So really what we're seeing here is a contribution, the source area of the watershed, when the Missouri River was more actively contributing to the 73 flood, that helped to explain greater thicknesses of sediment in the lower Mississippi River floodplain during that flood compared to the much lower concentrations in 2011. So along comes the 2018 flood. The time it was the third highest crest on record, now would be the fifth. Much of that water again came down the Ohio River watershed, and we were able to have our sensors in place, as y'all now know, to detect some of those kind of flood hydrograph patterns in the actual watershed. The 2019 flood, the third highest crest on record, but also importantly, the longest duration flood event on record of the lower Mississippi. You can see that during the early part of the flood here, most of the water was coming from the eastern side of the watershed. The little higher anomalous precipitation you see here would have gone down the Red River, which would not have made it to our study area. But as you saw the hydrograph continue throughout this long duration flood, the precipitation then shifted over to the central part of the watershed where more of the water was being contributed in from those western tributaries. And that's important in explaining some of the differences we see. So we went out and repeated some of our sediment deposits sampling in the floodplain areas that we sampled before in 2011 to kind of see how those match up to the 73 and 2011 floods. Interestingly, in 2017, we installed these sedimentation mats in these areas, and we were fortuitous enough to use GPS to relocate these after the floods. And just to make a long story short, it really confirmed some of our interpretations at other sites where we could not find those mats on the sedimentation thicknesses both in 2018 and following that in 2019. I will say that when we take a look at the data here, most of the samples that we were able to collect really had to combine the 2018 and 19 flood deposits because they occurred back to back, and really we couldn't distinguish between those two. And finally, the 2020 flood, another long duration flood in our study area, largely as a result of the Ohio River and the eastern tributaries contributing water and sediment downstream. So are these deposits different among different floods was our question. And we basically took a look at those and compared them to each other for all of the different studies that we have done. In 2018 and 19, the deposits, as you might imagine, it was a combined flood event, longer duration overall, were indeed thicker than we found in the 2020 flood. No surprise there. But when we normalize it by the number of days that these floods were overbank, it became a little bit closer. About 0.3 millimeters per day were deposited on average in these embanked floodplains with the combined 18-19 floods, and about 0.2 millimeters per day were deposited in the 2020 flood. One of the things that we need to think about are those changing source areas and the duration. So we'll take a look at this in a little bit. We believe that the longer duration events, of course, contributed to thicker deposits, but also because more sediment was coming in from those western tributaries in 2019, that also put in probably a little bit more sediment into the areas, all else being equal. So taking all four of these different studies combined, 1973, 2011, the combined 18, 19, and 20 floods, we can see that we overall had relatively coarse deposits in 2011 in terms of percent sand, especially as we get to the more distal parts of the floodplain. We also see that the combined deposits of 18 and 19 were generally thicker, as we saw before. And so we have different questions about what was going on, why deposits were thicker in 1819 compared to 20, why 2020 deposits may have been a little bit more coarse-grained than combined 1819. Well, of course, fine-grained sediments can be exhausted and flushed through the system. And so in 18 and 19, many of those were probably already removed and transported and deposited during those earlier floods, leaving behind mostly channel bed sediments for the 2020 flood to work with. So that explains some of the coarser sediments of 2020. But we also notice here during the latter stages of the 2019 flood in the lower Mississippi River, when those western tributaries were more involved, is that of the suspended sediment concentration occurring during those floods, a large part of it was actually silt and clay. So it was a finer grained sediment load that would have been deposited during the latter stage of 18 and 19. And when you combine those, that would have led to some of the finer deposits in 18 and 19 compared to 2020. When we take a look at this table and we again normalize these different types of deposits with the duration of the flood and also with the stream power, taking a look at how powerful the floods were, we can begin to tease out why we have different deposit thicknesses and whether we have percentages of sand that were relatively high. So in 1973, the very high percentages of sand that we saw in the actual river channel, 57% of the suspended sediment load was the sand fraction, whereas in the other floods that succeeded that, we had lower percentages of sand in the suspended sediment load to begin with. We can also see that the more powerful floods here of 1973 and 2011 with higher stream powers would also contribute potentially to more overbank deposition in the case of 1973 and greater amounts of sand in 2011. When we begin to take a look importantly at the average sedimentation divided by the number of days over bank, the sedimentation intensities have declined from 2.6 millimeters per day during the floods of 73 all the way down to 0.3 and zero point 0.2 millimeters per day of deposition in the more recent flood events. This parallels the declining suspended sediment loads that have been discussed in the literature along the lower Mississippi River through time. Finally, I'll take a look at some of these historical time frames in terms of how do these flood events match up historically, and of course that involves getting sediment cores in these same environments. And in 2015, we got shallow sediment cores down to about 2 meters of depth. In following up, the U.S. Army Corps of Engineers funded us in 2022 and 23 to go in with a geoprobe drill rig and get sediment cores up to a depth of about 6 meters below the surface in different environments across the floodplain. So in 2015, we didn't have much money for any kind of dating, but we could analyze those core samples for for their grain size amongst other variables. And in general, we see blue sands, red silts, and black clays. When you have going down the profile, almost all of these, in particular in these back swamp deposits, are showing coarsening upward sequences in the upper 1.5 to 2 meters of the floodplain sediment column. That's a little bit contrasting, as we know, with the typical fining upward sequence of meandering rivers. And this might be attributed, of course, to the more narrow embanked floodplain through time, which focuses more coarse grain deposits in a narrower area. Did the cutoff program play a role? Are more sands being delivered into the lower reaches of the channel because of sands moving from upstream? Could be related to the decline in those fine grain wash load coming down the Mississippi River through historical time frames. But we are seeing more or less some of these more coarsening upward sequences, especially in some of these more distal environments. Going out with the drill rig, and combining that with ground penetrating radar surveys, in this area I'll focus on. We did different areas, but I'm going to focus on this one zone right here downstream from Natchez. The embanked floodplain coming from the river kind of widens from the river, but then pinches back close to the river, and that's where we were actually getting our drills in, or our cores in. And you can see the layout that we have, where we have a GPR profile between these three cores, another GPR profile between these cores in a more north to south orientation. So the GPR profiles in this area show pretty homogeneous laminated overbank vertical accretion deposits, both north and south and east and west. Now looking at those floodplain cores, we can see there's not as much upwards coarsening or fining type of variability in them. They're a little bit more alternating between sand silt, reflecting very likely energy associated with different flood deposits. And now combining these correlations using GPR and grain size from different cores, we can see basically the patterns of sedimentation historically speaking now. These are bomb pulse radiocarbon dates that we extracted that we trust from these different cores. And notably, we can see that we did elevation kind of surveys from core to core. The Mississippi River is to the left side. The bluff line is to the right side. We actually have elevation profiles dipping in the direction of the Mississippi River here, where this embanked floodplain pinches in. These are kind of a new type of a deposit that I'm referring to as overbank return deposits that might be unique to overbank flood or embanked floodplain settings, where sediments are continuing to be deposited by major floods as they exit the floodplain and re-enter the channel and actually kind of drape toward the river channel, depositing these different layers. But we see these dates extending back from the 1800s to the 1980s, up to the surface here, where we have dates of 2012 and 14. We can delineate in what we believe to be the 2011 overbank deposit and the 1973 overbank deposit. We can also get that other transect going from north to south and take a look at the sedimentation rates that we expect. So if we use the long-term 1800s that we trust sedimentation rate with the thickness of the cores, we see that that ranges from 2.5 to 3.5 centimeters per year. Using the 1973 flood as a marker, that averages about 4 centimeters per year. 1984, if we use those dates, 3.1 centimeters per year, and then the 2011 marker, somewhere between 3 to 4 centimeters per year core to core. So really we see that there might be a little bit more rapid sedimentation occurring here but pretty close to the long-term historical rate. So my conclusions are the following, and I know that was a lot to kind of digest, but I'll reiterate what we believe to be the case here. In the embanked floodplain during major flood events, sand deposition near the channel, but we have gradual settling of muds as they move across the embanked floodplain, and even some of those overbank return deposits where overbank waters rejoin the actual floodplain. The source of the flood is very important. Sediment-rich tributaries like the Missouri River result in more deposition in the floodplain, but the grain size tends to be finer grained compared to when you have more energetic floods that do not have as high suspended sediment concentrations. The flood magnitude and power definitely influence the grain size of the overbank sediments. More sand percentages that go from even into distal floodplain environments. The duration and timing are very important. In fact, duration we would see is probably the primary factor for overall rates of sediment in terms of being deposited. Not necessarily the sedimentation intensity, but certainly the overall amounts of sediment in the floodplain. Historical sedimentation rates show that the sedimentation intensity per flood has been declining since the mid-20th century, probably as a result of lower declining suspended sediment loads in the river channel through historical time frames. The fact that those longer-term annual sedimentation rates going back to the early 20th century and 1800s are close to recent rates are potentially resolved by the fact that we're getting more frequent and long duration floods in these study areas. Remember, these are annual sedimentation rates, whereas we end up having long duration floods that continuously supply sediments might be different now that we have an embanked floodplain. A more limited flood-prone area that concentrates sediment deposition could also explain why more recent rates match the long-term annual sedimentation rates despite flood sedimentation intensities declining. Is the sieve clogged? There's plenty of accommodation space as we've seen by flood depths in this inundated floodplain going down, in some cases, 7 to 8 meters of inundation during major floods. We also see that declining suspended sediment loads through time don't pose as much of a threat to the overbank floodplain environments. There's a lot of room still for that water during a flood event to be stored, which basically resolves that either the channel is potentially aggrading. It's not the floodplain that's really responsible for climate change issue, where hydrology is to explain why we're getting more intense floods in these study areas around Natchez. I do want to thank a lot of the graduate students that have contributed and colleagues that have contributed here to this research through the years. Funding from the National Science Foundation, the Nature Conservancy, the Geological Society of America, and the Corps of Engineers. And with that, I'll be happy to take any questions. Thank you.
That was super. Thank you so much, Frank. Everybody in the audience, the chat is now open for you to please type your questions there. Make sure that when you send them to everyone. You can see that in the drop down of your chat. And please tell us your name and where you are watching from. That's always just nice to see where, SEDS Online is spreading its reaches. So please send those there. In the meantime, this is my favorite because that means I get to ask a question, and I have a bunch. So I was curious, and I probably because my brain is a little bit like in teaching mode right now. So I'm wondering, in terms of the drainage and the flood response, sort of you had a slide where you show like a 4-step flood response. And I'm curious how that flood response you might expect it to change with slight changes in the slope of that the overall slope of that drainage basin.
Yeah, no, that's a great question. And as you saw from that slide, there are very profound elevation differences on the order of meters between one part of the embanked floodplain and the other.
Mhm.
And so the natural levee, the crests are about 19 meters above sea level in that vicinity of that slide that we looked at. But a lot of those other distal environments were, 11, 10.5 meters above sea level. And so any point at which you have basically a low part of the channel bank, in particular where some of these kind of Yazoo tributaries join the Mississippi River, those are locations where backwater with fine-grained suspended sediments can push back upstream almost or up gradient as you begin to have stages rise in the actual main river channel. But those, of course, are before crevasses are activated and certainly well before natural levees are overtopped. So one thing that we noticed was that this kind of progression of backwater moving up gradient as the river channel rises during the rising stage of the hydrograph right there, you really see relatively slow moving water bodies that are pushing backwards, and those potentially could be very important in depositing suspended sediments, fine-grained suspended sediments, in many cases because we see the peak sediment concentration in the river on the rising limb of the hydrograph, and we see suspended sediment concentrations of the river lower on the falling limb of the hydrograph. And so by pushing some of that higher concentration sediment up into those low-lying areas, those are an important contributor to floodplain deposition. As soon as those crevasses are breached, the elevation, the stage of the river begins to penetrate through those natural levees, we immediately switch to down gradient flow directly across the floodplain. And it actually doesn't necessarily adhere to the meander bend curvature and the orientation of the river's meanders. It's basically moving across the entire floodplain, irrespective of the channel, in a down gradient fashion. So that kind of reverses the direction of sedimentation, potentially even remobilizes some of the sediments depending upon the energy conditions across the floodplain, and can then redeposit them downstream on the floodplain or even return them back to the channel itself. Did that kind of help explain your question there, Chelsea?
Yep. Yeah, absolutely. And it got into one of my
Okay,
other questions. So,
great.
um, two birds. Okay, we have a question in the chat from Joanna. Hi, Joanna, watching from Colorado. How transferable are your findings to other large engineered rivers, for example, the Rhine River?
Yeah, that's a great question. And the one that I think of that is comparable along these embanked systems would be the Rhine. The Rhine, of course, has been managed differently than the Mississippi in terms of strategies for flood prevention. But there are certainly similarities. So I know that the Room for the River project, for instance, in Holland, has been designed to move back and set back some of these artificial levees to allow for a broader region of inundation. So if that's the case, I would expect, therefore, some of the stream powers to be a little bit less than those experienced in this very narrow kind of funneled area of the Mississippi River, which might result in more fine-grained deposition along the Rhine, and potentially less sand distribution to or more distal parts of the floodplain along the Rhine. But I do expect that it is a good pair. Those two are certainly could be investigated. Of course, the Rhine also experiences a greater tidal kind of influence than the lower Mississippi River does, but our area is further upstream from the tidal influence along the lower Mississippi. So areas downstream, closer to Rotterdam, would be a very different type of a study that would have to include more tidal influence there. But I do think that in general, what we're looking at is these embanked floodplain corridors. We're trying to provide a model that might differ from if the floodplains were very wide, and trying to figure out what we expect to see. An applied part of all of this work could potentially be if floodplains need to be excavated, and I know that that's been part of the Room for the River project to basically increase flood conveyance capacity. What do you do with that sediment? What is the type of sediment that you have? Is it appropriate to go to shoreline restoration projects? If it's very organic rich sediment, is it appropriate to put back upstream to for farmers that have had fields that have been eroding through the years in areas like Iowa, Minnesota, Nebraska? What do you do with it if you do decide to increase that flood conveyance? in these embanked floodplain corridors, which is of concern for the long-term sustainability of those programs. I hope that
Yeah,
answered the question a little bit.
I think so. If you have any further questions, Joanna, just put them in the chat. Okay, one more question in the chat. Thanks for a fascinating presentation. You mentioned these water bodies pushing back upstream. Do these ever interact with later pulses on their way downstream? And that's from Stephen watching in Derby.
Yeah, great question. So, interestingly, I was in the floodplain when we were having a rise of the Mississippi River, and I was right along the banks of one of these kind of yazoo streams. We call them Batcher channels, and really observed during the rise of the channel, watching the water flow, quote, backwards, right, up gradient, and moving into through a channel and beginning to inundate some of these low-lying floodplain areas. It was a very slow, kind of a gradual flow. It wasn't very dramatic, but it was very detectable. So, in terms of when those crevasses are breached at a later stage of the flood hydrograph, those would certainly overwhelm any of that backwater that would have been making its way over. It would have been a much more energetic contribution of overbank flow, of course, that reverses direction, quote, of some of that sedimentation area. So the sediments that would be deposited by a backwater kind of inundation would be fine grained, giving them a chance of preservation because of their cohesive nature. And then, if inundated deeply enough, the lower areas would be those that would preferentially preserve that as the more rapid kind of overbank or crevasse activation would be able to reverse flow direction per se. So areas that would be shallow backwater or inundation areas would be those that are more subject to maybe being reworked and redeposited somewhere else. I hope that maybe addresses the question.
Yeah, absolutely. Did for me. Okay, I think we are gonna have to call it and hopefully we can stay on because I have some more follow-up questions. But
Sure.
thank you, Frank, so much for your time and for giving one of our SEDS online webinars. Thank you, everybody, for joining. We are grateful to have you here, and we hope to see you next month in November on the 12th, where we will have our student webinar. So in case you're unfamiliar with that, we have student webinars where 3 to 4 students present their work. They send in a very short abstract. So make sure and check that out online and tell your friends. Thanks so much.